Hi guys, my name is Dmitry and I welcome you on my technical channel. Today we are going to continue our experiments with FPGA using RTZ7 board. In the previous tutorial we finished minimalistic implementation of a video controller for a retro computer from the past, which was called ZX Spectrum. Some of you may know that it was a legendary machine, yet it was very simple. So having video controller implemented is pretty much half of the original hardware. This is why eventually I decided to make a fully functional retro computer on the RTZ7 board. The challenge was to avoid using soldering iron and additional hardware modules, only original platform from Digilent, nothing more or less. After publishing the tutorial about ZX Spectrum video controller, my initial intention was to have a series of YouTube videos thoroughly describing the other components of the retro computer. However, a few of my subscribers expressed some confusion and lack of interest for such approach. They told me that such a level of detail reduces audience retention and makes it more difficult to navigate between multiple videos while keeping track of the goal of the project. In my attempt to address this, today we are going to walk through the entire ZX Spectrum on Zynq project. Some of you may raise concern about the practicality of all this. Is it due to nostalgic reasons? And if not, what is the purpose of learning old, long-time, obsolete technologies? Nostalgic feelings are just emotions, and I would like to remind that my channel is technical. As for the obsolete technologies, we don't use them. We use neither old ICs nor CRT TVs. Our retro computers won't need a cassette tape player or a physical floppy disk drive. Instead, we implement old hardware on modern platforms and integrate them with modern equipment and peripherals. Think about a possibility of seeing a picture generated by a reincarnated home computer from the 80s on your modern HDMI monitor, while realizing the fact that the computer was designed to work only with old analog CRT TVs. How about modern wireless USB keyboards, which you could interface with your retro computer, taking into account that the USB standard was born long after the last computers from that era had been discontinued. Besides, learning how the old digital electronics was designed several decades ago and learning how it is designed and function nowadays give a tremendous boost in terms of knowledge and skills. Not to mention, it is a lot of fun. And yes, working with old technologies is nostalgic. Well, a little bit. Have I convinced you and motivated enough? If yes, let's start. So let's start looking at the project and more specifically at the high-level block design. As you can see, it comprises of two big halves, PL and PS. On PL, we have a logic implemented on FPGA side. On PS, we have embedded C application running on one of the ARM cores. And as you can see, they are interconnected through dynamic RAM and through registers. So we can control hardware on the PL side by means of registers, and then we share access to DD RAM, which allows us to run C application which physically resides in dynamic memory. So on the PL side, we have board design components colored in bright yellow, board design component. We have two buses, two AXI buses. One is AXI light. This is the AXI light, which is standard way of organizing access to registers. And the second one is just AXI interface. It's like full interface, which allows to do memory to stream and stream to memory operations. When it comes to VHDL modules, the cornerstone of the whole design of the ZX Spectrum is Z80 CPU. Its implementation we took from OpenCore's resource. At the moment it is the most accurate and standard model of Z80 microprocessor. We have a clock generator that generates standard 3.5 MHz clocking for ZX, standard clocking for Z80. Half of it, it's 1.75 MHz, is used to clock the sound chip, which is AY8910 or its replacement YM2149. We also have ZX sound mixer, which mixes output from the sound chip. In fact, it has 3 channels, A, B, C. We have output from beeper, and then we have output from tape cassette emulator. Each channel has its own weight, so potentially we can control volume of each channel individually. It gets mixed, the resulted signal goes into PWM module. The output of it is hooked directly to the RT-Z7 board, more specifically to the low-pass filter with mono audio amplifier, and after it goes to the audio jack. We're going to have a closer look at the principle of this block. The I/O ports encoder decoder allows to organize a few standard ports for ZX Spectrum. One of the bits of the port is used to organize beeper. One of the bits is used to emulate tape recorder. This encoder is also used for interfacing with ZX keyboard. The tape emulator is a custom design which didn't exist in the original ZX Spectrum. The need for this is justified by the absence of a conventional tape recorder. We still need to have a way of downloading programs the old way, as if we have a proper tape cassette recorder. This block is responsible for video generation, and also it has a set of control registers which allow to set specific parameters for the video output. Also, it is used for configuration of different options of the computer itself. As you can see, ZX control is interfacing with axial light interface, and through the set of registers we can configure certain parameters of the computer. The output from ZX video module goes straight into axis stream to video out BD component, and then to RGB to DVI. Then we have a standard data stream for DVI or HDMI interface. The timing generator and the data get mixed in axis stream to video out, as you can see, and as you probably remember from the previous tutorial. Now we also have GPIO HDMI component, which is used for HPD, hot plug detect. It is just one bit, just one GPIO, which goes straight into HDMI source and connector. AXI dynamic clock generates a serial clock which is used for RGB to DVI interface, which is used for RGB to DVI component, which is, if you remember again, 5 times faster than the pixel clock. On the PS side, we have functionality grouped into several entities. One is ZX Spectrum Video. This is a low-level driver, Zynq Video, Zynq USB, Zynq File I/O. Those drivers are port specific. The ZX Spectrum Video is like a platform agnostic logic, so potentially it can be easily ported in case of changed hardware configuration. And we have ZX Spectrum File I/O functionality. Let's have a closer look at each of those subcomponents. As you can see, we have a ZX Spectrum display control, which through a low-level driver interacts with the video subsystem. It configures refresh rate, it configures resolution, it configures the start address of the video memory when we switch video pages, for instance. ZX Spectrum Video is a high-level logic which hides complexities and intricacies of this block. We also have 3 different fonts which we use for a shadow page, a shell page if you like, which uses those fonts. So the standard Spectrum doesn't know anything about those fonts. This is for shell needs only when we interrupt the execution of standard ZX Spectrum program, and then we switch to shell, which allows us to choose, for example, which program to load into the Spectrum, which screenshot to load, and things like that. ZX Video block also has dynamic clock driver, which again through the registers configures the dynamic clock. Zynq USB logic. At the heart of it, there is a tiny USB stack which we manually ported from a GitHub project. It has a single host driver, which is HID, and it interacts with the keyboard mapper. Mapper converts the scan codes coming from HID host driver and writes to specific registers to emulate standard key presses for the ZX Spectrum keyboard. Now the files, the programs for the ZX Spectrum are kept in microSD card. That file system accesses the content on SD card through a glue logic, which is SDPS driver designed by Xilinx. The files can be in one of those 3 formats, snapshot, and 2 formats for the tape images. The tape reader reads the content of files and puts into FIFO through the registers, and then it gets access through another FIFO which pushes data into tape emulator. So it converts bytes into audio signal if you like. And so the ZX Spectrum computer is under impression that it loads a program through a standard tape interface. The text shell, as I mentioned already, is used to navigate between the files on SD card and organize data download. This is pretty much it on the top level, and let's have a look at the project itself. So let's open the block design. And you can see that it hasn't changed since our previous tutorial. The only thing that we need to make sure of is configuration of PS block. So we will need USB 0 at least, SD card, UART is always enabled, and this is it. Let's switch to the file system and have a look at the constraints file first, and then we can see the same pins that we used in the previous tutorial. Those are dedicated to HDMI interface, but we also have a couple of new ones. So this is audio output, and this is also a pin that enables or disables the audio output. If we go to the schematics, so this is our signal audio PWM. It enters the amplifier, and the output from FPGA is R18. This is R18 indeed, and we also need to have a look at audio SD T17. This is T17. Audio SD controls the output of the amplifier and the low pass filter, the whole analog circuitry. Now let's go back to VHDL sources. There is a dedicated folder for Z80 softcore. This is taken from OpenCores, and this is probably the best, and if not the only, proper implementation of Z80 state machine. Now we have ZX address data bus, which is actually writer and reader. I still need to rename this module. This is only mapper. Let's have a look at the actual logic. So we have AXI interface, and then we have interface of the memory mapper, which allows Z80 CPU to access RAM through our AXI writer reader. And those are the signals to control configuration. at the moment we don't even use it. Probably I need to remove it. It was used during the debugging stage. AMBA specific constants and a simplified AMBA state machine. Extremely simplified. So there are typical states to interface with AXI bus, idle, set address, address acknowledged, start data, and we have separate data flows for writing and reading transaction. This is defined by the signal. There is also one interesting moment. Z80 is 8-bit microprocessor, while the AXI transactions are 32-bit minimum. So if we want to write only 1 byte, we use an additional auxiliary signal, which is called strobe, STB, I think. Yes, right, strobe. We set it to 1 at the beginning of our transaction, and then the next step we immediately set it to 0. So strobe signal is represented by 4 bits, and then, as you can see, we manipulate only with 1 bit, depending on whether the address is odd or even. We set only 1 out of 4 bits, which would mean that we will be writing or reading only 8 bits out of 32. And this is it for this module. Going to the next module, which is the text main. We have an interface to interact with AXI reader and writer. Those are our registers and some auxiliary inputs and outputs. Border color is latched by standard ZX register, and it goes to our video controller. Same about border strobe. A new frame interrupt comes from video controller, although it's not exactly the right implementation, but we will talk about it later. Same applies to EULA attribute. It simulates the standard behavior to the best abilities, but it's not cycle accurate. Audio output, audio enable, and a signal to switch to shadow video RAM, which is Spectrum ZX 128 specific. Yes, this is port 7FFD, bit 3. 3 normal or shadow screen to be displayed. This is a standard attribute of ZX Spectrum 128 configuration. Now we have a few constants: the volume of audio beeper, the volume of audio tape signal. We have quite a few signals to interface with Z80 CPU, clocks and additional signals to control CPU, signals for a Y sound chip. Those are our registers. In fact, those are constants. More constants related to ZX Spectrum standard ports, and then the actual ports. Signals are related to tape in-out, a FIFO 16-bit wide and 1K deep. This is the instantiation of our FIFO, which is used for tape emulation. This is the instance of Z80 CPU. This is the instantiation of audio subsystem. We will look at it later. As you can see, we don't support non-masked interrupt at the moment. This is interrupt generator, which is supposed to trigger every frame, every video frame. This is a little bit cheating, so we just pretend to behave in the standard way. It's not clock cycle accurate, so not all games will be properly supported. But in this project we are focusing on simplicity. So this implementation of the ZX Spectrum is not going to be 100% compatible with the standard model, be it 48K or 128K. Tape loader emulation. We simply fetch the next element from FIFO, taking into account several signals, and push it into standard port. Clock enabled generator. We generate 3 frequencies, 7 MHz, 3.5 for CPU. This one is not used at the moment. This is going to be used for turbo modes. And clock for the sound chip, which is half of 3.5 MHz. The way how we generate clocks is in essence enable signal. So all our components are clocked with the same clock, but we choose a duty cycle, if you like, by manipulating with enable signal. Enable signals are driven by clock 7 MHz, 3.5 and 3.5 divided by 2. This is some logic around generation of hold signal, hold acknowledgement. Again, it's not ideal, but for now it works, and for now we will leave it like this. And this is the main state machine of this ZX Spectrum itself. So we support some limited number of ports to handle keyboard, to handle hardware which is configured by standard 1FFD port by 7FFD port. We also support the data flow for the tape emulation, and those are the registers which we use to retrieve the state of certain signals, which is used to support our SNA format when we need to restore certain registers of our CPU. Restore and backup. Control signals for ports, for FIFO. Logic to control the data bus of the CPU, and this is for writing into the registers. Standard ZX Spectrum ports and our internal registers, which are part of our state machine, if you like, which is not a standard ZX Spectrum. And this is the same logic for reading registers. Interaction with memory, and this is pretty much it. As you can see, audio is permanently enabled. So this is the architecture of ZX Spectrum 128 kilobyte, simplified as much as it could be simplified, yet still capable of running most of the games. Going to ZX sound, we have a PWM module which does the conversion of 8-bit values into PWM representation. Very simple. This is a cleaned up version of sound chip, AY sound chip, which was originally designed by Seed as part of Spec 2010 project. All we did, we just cleaned up the code, and the functionality is still the same. I tried to find the original source code for Spec 2010, but I don't think I managed to do this. This guy is not the original developer. This guy took the original code and enhanced it to support, mainly to support div MMC interface, and added capability of running ESX DOS. This is the original thread which was created on ZX PK resource. So as you can see, you need to be able to read Russian in order to understand what is going on. And again, this is the sound mixer which was originally taken from Spectrum 2010 project. Again, we simplified and cleaned up a little bit the whole thing. And this is the mapper, which instantiates all our components: the mixer, the sound chip, and the PWM block. We don't support turbo sound, which means we have only one sound chip. This is the equivalent of AY chip. Now we go to the video subfolder. Again, top is just a mapper. We instantiate ZX control and ZX video. ZX video, this is the logic that we enhanced a little bit, but in essence it is based on our tutorial, which is a ZX Spectrum video controller. Again, not clock cycle accurate, but this is the first reincarnation of this video controller, if you like. And the ZX control, this is basically the logic that allows us to configure certain blocks of our hardware, our emulated hardware. So we have registers to configure the video controller. As you can see, we have registers to pass information from our embedded C project to the standard registers of ZX Spectrum. For instance, we pass keyboard scan codes, which originate from the USB host. And obviously it's not an original implementation of the Spectrum. This is why we have this additional infrastructure around it. And finally, this is a wrapper around the whole project, and it interconnects our logic with the board design. External signals are the same as we used them in the previous tutorial for video controller. The only difference is that we added two signals related to audio generation. AXI interface, AXI light interface. Yeah, so this is AXI interface to provide access to the memory for Z80 CPU. So we instantiate video controller, we instantiate AXI writer reader. This is that one. We instantiate ZX main top. And those are just signals for the interconnect. That's pretty much it on the VHDL side. Now let's have a look at the PS side. This is a free RTOS project written in embedded C. At the top level, as you can see, we have not so much. We initialize the main thread and we start the FreeRTOS scheduler, and then we simply go to the main thread. We initialize video, disable caching for specific segments in memory, initialize some signals for the Z80 CPU, initialize SD card and USB host interface, and then we continuously handle events from the USB stack and the ZX Spectrum tape emulation functionality. We also have a callback function for HID driver, and here we do a conversion of HID scan codes into ZX Spectrum representation. Version is just for the sake of being punctual. Let's go into ZX Spectrum file IO folder. But before we do so, let me point at the naming conventions. So as you can see, we have a few folders starting with Zynq. This is so-called low-level drivers and functionality for this particular platform. And those folders, they contain functionality which is mostly about Spectrum machine, Spectrum hardware, which is more high level than those drivers. Let's have a look at this folder first. It has implementation of FIFO in software, which we use for ZX tape emulation. ZX shell is a piece of logic that allows us to stop the emulation, activate a shadow screen, and display certain information. Well, mostly it is the content of SD card to navigate between the files and then initiate loading process. Snapshot, it is to support SNA format. Again, it is based on the logic which was originally developed by Seed for Speccy 2010 project. We significantly reworked this. We reworked it and cleaned it up a lot, so it doesn't look ugly anymore. Well, the most interesting part in this logic, I would say, is the way how we restore registers and then how we restore the program counter. The interesting aspect of SNA format is that we take a screenshot of the full memory available on Spectrum, which means that we don't have a single byte that we can use to do additional work. Everything is a snapshot, and we still need to execute our code to restore registers and to restore the program counter. To do this, we have this logic, ZX snapshot load page. Yeah, this is basically the code that we load first. We restore, it allows us to restore registers, and then it is looping forever. Then the next step, we simply restore the content of RAM, and then at that point the program counter is in stack. But in order to get that value from stack, we need to execute this opcode, which is return. As I mentioned, we can't modify RAM anymore, so for this trick we do the following. We scan the ROM for the presence of any random C9 opcode, and then we simply force the CPU to jump to the specific address. As a result, it fetches the next value for program counter, which is stored in stack, and then this is how the whole snapshot starts to execute. This is the implementation of tape emulation. Again, it supports specific two formats to be more exact: TAP and TZX. The last one is more sophisticated. It can contain more than one binary block, and then it can support multiple speeds and so on and so forth. But in essence, what we do, we read a byte from the data stream. We read a byte from a file which is stored on SD card, and then each byte we convert into a specific value, and then we push it to the FIFO. And then on the PL side, elements are fetched from FIFO, and then it basically emulates the behavior of tape. So this is why the ZX Spectrum hardware is under impression that it works with the real cassette tape. Next piece of logic is ZX Spectrum I/O. This is mainly for the conversion of HID scan codes into appropriate values, which can be understood by the standard ZX Spectrum machine. In total, there are 8 registers on ZX Spectrum, and then as you can see, each register is responsible for specific keys. So this is the magic basically. We need to convert scan codes from HID interface into combination of those 8 codes and write them into appropriate hardware registers. And this is the logic that does that work for us. We also reserved a possibility to support a standard HID mouse. So through this we can potentially emulate Kempston mouse for the standard Spectrum, but that will be our future project. The ZX Spectrum video contains logic to interact with the video controller running on the PL side, so we can specify certain parameters like scaling factor for the ZX Spectrum frame, resolution, this is related to HDMI resolution, and so on and so forth. We can even change border color through this API. This is a little bit of glue logic around Zynq driver. We initialize display, we prepare memory, which is going to be used as video memory, and then we start video controller. This is the logic when we switch to a shadow video page to support shell, and this is the way of manipulating with start address of the shell. For our shell we have 3 different fonts. All of them at the same time can be used. Some specific constants and then structures of each register. As you can see, we can do a lot of things. This is reserved for future, that at some point we're going to add support of TRDOS and then video controller specific settings, so on and so forth. So this is a little bit of low-level logic. This is a FAT file system, and this is again the glue logic to interface it with the hardware. So the file system allows us to store data on SD card in a conventional way. We can potentially support FAT16, FAT32 file system, and the content of the SD card can be written on any PC and then can be read by the ZX Spectrum emulator. This is from the original display driver. It instantiates and starts timer. This is the stack, the USB host logic, the USB stack, which is based on tiny USB project, and it was ported by us, and at the moment we are using HID host driver to support standard USB keyboards. And finally, there is a bit of logic around display controller and dynamic clock, which are part of PL. As you can see, we support several video modes, which is related to HDMI standard. So let's try to compile and run the application. Let's have a look at our test setup. It is RTZ7 board without any additional hardware modules. There is HDMI cable connected to HDMI out connector. This is the wireless USB keyboard, and this is the keyboard that I'm going to use. The micro USB connector, which supplies power and data lines. It allows to JTAG the board and see serial output. And this is the audio jack connected to line in of my PC. So let's have a look at the project. I have already built Vivado project, exported the HDF file to SDK. In SDK, I already updated the HDF file, so the project is fully built. Now what we are going to do, we're going to provide a test ROM for diagnostic purposes instead of a standard ZX Spectrum ROM, and we will try to run and see what happens. Let's do that. So everything is ready. Let's JTAG the project and see what happens. I'm switching my camera, and we should potentially see output generated by the board. And yes, our test firmware was able to run. So this is the code which is executed by Z80 CPU. And then looks like it is happy, at least to a point when it is capable of running and capable of testing RAM pages. So far so good. Test number 2, test number 3. Preliminary tests passed. Okay, let's test our keyboard. And yeah. Working fine. Enter. Yes. Caps. What is the name of these caps? I think it is shift. Okay. And I'm not sure about those two remaining buttons. Yeah, I will need to double check on those two keys in the last row on the right. Maybe it's because of my keyboard, which is not full. Okay, let's go back. Space. Ah, okay. Space. This is space. Fine. Test passed. We don't have Kempston, so let's test the second item. Seems to be okay. Speaker test. Internal ROM test. Yeah, okay. It's not gonna work. More RAM tests. I'm not sure if I pressed 5 twice. It obviously takes some time. Yeah, it was 5. Upper RAM refresh test. Upper RAM scanner. Let's start with the beginning. And I guess it's interactive. 1, 2, 3. Invert 4. Rotate 5. Sort of. I guess. Again, and upper RAM code execution. I'm not sure what it means, to be honest. Yeah, I'm not so sure what it is going to test this way. Let's not wait and let's restart the whole test. So, RAM tests, silent. Let's not go to this because there will be some level of incompatibility of our system with the original Spectrum. Let's do system EULA tests. Yeah, input stays low. This is because we don't have a real tape recorder. We don't really support that bit. Floating bass effect, sort of. We are emulating it at least. Port 254, the decoding test. Black and monotone should be heard. Yes, this is what we have. Z80 analysis. Okay. Mic test we're not gonna use. 50 Hz interrupt test. Let's test it. It should scroll smoothly. Well, hard to say. Interrupt frequency high. Yeah, that's not very compatible. Let's put it this way. Snow effect we are not going to have because we don't emulate the full hardware. Data bus test. Let's do data bus test. Don't know. Spectrum 128 menu 7. Memory test, video buffer test. Okay, let's do memory test again. Okay, AY sound chip test. And then we should hear some sound. Which we do. Nice. Contention test we can try, but it's not gonna work properly. Yeah, it's not non-standard system. This is what I was talking about. We don't support the. We don't really have a fully compatible system. Okay, let's try to start the standard firmware. We need to replace the ROM, and what we do, we're going to use Pentagon ROM. Remove and see what happens. And we can see proper startup menu of a standard ZX 128K Spectrum. Let's hit F11, F12. And this is the list of files that I have already put on my SD card. This is just an example. So this is the way how we navigate through the list of files. This is using our shadow video page and the functionality of shell. One of my favorite games, Snapshot of Silkworm. And as you can see, it works. Let's start again. Yeah. Even though it is not fully compatible system, you can see that it is quite possible to use it for ZX Spectrum games. Not all of the games are going to work on this system, but this is going to be our next challenge. So this is all for today, folks. I hope you liked the video. Please hit subscribe button. Please like it if you liked it. And till the next time, bye.